Now, I really recommend that you get good at sketching modulus graphs. It's going to really help out when you need to solve modulus equations, modulus inequalities, and just modulus questions in general. So I'm going to go through a rule that you can use to sketch graphs that look like this. Y equals modulus of something times x plus a constant. So firstly, these graphs are going to be V-shapes. The vertex is going to be at x equals minus b over a, and the reason why is because if you make this ax plus b in the modulus brackets equal to 0, rearrange that, you get x equals minus b over a. And the y-intercept is going to be the magnitude of this b value. So if b was minus 2, the y-intercept would be 2. If b was 3, the y-intercept would be 3, so the modulus of that b value. And also the gradients are a and minus a. So for example, with this V shape here, right? So the gradient there could be a, the gradient there minus a. So they have the same magnitude. So these V shapes will be symmetrical. Obviously my diagram there is not perfectly symmetrical, but they should be symmetrical. So as an example, what will this graph look like? So I know that my vertex is going to be at x equals 2 over 3. So make this equal to 0, right? Rearrange it. X is equal to 2 over 3. So I'm going to have my vertex at 2 over 3. Now the gradient here is going to be 3. The gradient there is going to be minus 3. How do I know that? Well, look at this m value there, right? So gradient 3, gradient minus 3. Now my y-intercept, I know that's going to be 2. Must be 2 because, again, of what we said up there. So again, another example, what will this V shape look like? Well, again, we're going to have a vertex when x is a quarter, okay? Make this equal to 0, x is equal to a quarter. That's going to be our vertex. We're going to have a gradient of 4 and minus 4 because that's our m value. And we're going to have a y-intercept of the magnitude of this minus 1, which is 1. So vertex there, y-intercept there, some kind of V shape like this. Now let's think about some graph transformations. So obviously if I put a minus sign in front of there with this first example, what's going to happen? Well, we know from graph transformations that when we put a minus sign in front of the function, we just flip the function upside down. So literally this just flips upside down. That is now minus 2. Now going back to the example 2, what if we put, let's say, a 2 there and a minus 1 there? What would now happen to this graph? Well, firstly, we need to multiply the y values by 2. So we're stretching the graph in the y direction by 2. So the graph is going to get 2 times steeper. So that's step 1, multiplying by 2. But now obviously we've got the minus 1 there. So now we shift the graph down by 1. So we're going to end up with something like this. So we've literally just taken this blue V shape and just shifted down by 1. And that graph at the bottom is our final answer, and that's what you would sketch for your final answer. Now, what if you had to sketch something like this, where you've got a modulus of x, but that's kind of trapped within more modulus signs? Now, I'm actually going to use a numerical example to show you how I would work with this question. So I'm going to start with y equals modulus of x. Just going to forget everything around it. Just focus on the modulus of x graph. Now, what does that look like? Hopefully, we are comfortable that that is just a normal standard V shape like that. So again, if we just ignore the modulus brackets here, right, what's happened is that we're going to multiply the y values by 2. We're going to stretch in the y direction by 2. So stretching this. So again, this is y equals modulus of x, the black one. When we double that, the y values double, so we get this blue one. Now we're going to take away 3. So again, we just shift down by 3. So when we shift the blue one down by 3, we get something like this red one here. Now, what we're going to do is we're going to take a modulus of this red V shape. I'm going to redraw this red V shape somewhere over here. So just redrawing this here. Now, we're going to take a modulus of this. So remember, the modulus of a value is the magnitude of the value. So the magnitude of all these y values here, obviously, is just the magnitude of the y values there, right? So these y values aren't changing when you take the modulus of these y values. But as soon as you hit this x-axis here, we've now got negative y values. So negative y values trapped between here and here. So what will happen when we put the modulus signs around here is we're going to have exactly the same here, but now we're taking the magnitude of these negative numbers, so we're just going to flip like this, and we get a kind of W shape like that, where that is 3. Now, the whole reason I want you to get good at sketching these modulus graphs is because if you do have a question where you need to solve an equation with modulus signs, I highly recommend that you sketch the graph. So you sketch this graph, y equals 2x plus 1, which you know how to do from GCSE maths, hopefully. And then you can sketch this graph, this modulus graph, using the same kind of logic that we have used today in this video. So you've got y equals 2x plus 1, this straight line graph from GCSE. And then again, the vertex of this V shape, okay, is going to be x equals 8. Make this equal to 0, add 4 to both sides, times by 2, you get x equals 8. That's our vertex. Y-intercept is 4. So we end up with something like this. Now, clearly we can see from the graph, because it's pretty obvious, that we only have one point of intersection, this point here. So there is going to be only one x value that satisfies this equation. So your objective with this question is to try and find that. So you're going to make 2x plus 1 equal to the left hand side of this V shape, so this straight line graph here, and this straight line graph is going to be y equals minus a half x plus 4. You're just literally taking the negative of everything inside there. Linear equation, GCSE maths, you're going to work out this x value there. Now, hopefully I've done my working out right, but I get x is equal to 6 over 5. So that is the solution, x equals 6 over 5 as a final answer. Now, some people and some schools teach you to do a slightly different method. They may teach you to do an algebraic method where you take the equation and you square both sides, because when you square modular signs, you actually remove them. And that's just because when you square any number, you can never get a negative value. So when you square a modulus sign, then the modulus sign just disappears because you don't need it anymore. So you would write this, right, square both sides. Again, as I just said, when you square the modulus of something, you don't need the modulus signs anymore because the square of anything is non-negative and the modulus of anything is non-negative, so you don't need the modulus signs. You can then expand your brackets on both sides and rearrange to make equal to 0. Now, when you do that, you should end up with something looking like this. I'm just going to times both sides by 4 to get rid of this fraction. So you end up with something like this here. Now we can go to the calculator, solve this, see what we get. So the A on the calculator is 15. So just plug in here 15. The B is 32. So plug in 32. And the C is minus 60. So minus 60. Now if we solve that, oh, we've got two values, right? So we've got 1.26 over 5. Yeah, we got that from the graph there. Now we've got this extra one. Okay, now hopefully you can see from this graph here, there should not be an extra solution, right? Because obviously, look at this graph here. The gradient, there's 2. The gradient here is a half, right? Gradient half. You're never going to intersect again, obviously, because this gradient there is more shallow than this one. This one's going to diverge away, and this one's going to kind of go over there. But the calculator is telling me we've got an extra solution. This is the problem with this method. The problem with this method is that when you square both sides of an equation, sometimes you create an extra real solution. So what has happened here, we've created an extra real solution that does not actually solve the original question. So you could do this method. There's nothing wrong with doing this. But if you are going to do this method, be aware that sometimes you may get an incorrect value. So what you need to do, if you are going to use this method, you need to take both of these x values and you need to plug both of them back into the original equation. And you need to make sure that the left-hand side equals the right-hand side. And if it doesn't, then you know that one of these solutions is wrong. So you plug in 1.2 there and there. You should get the same thing because clearly from the graph you do. Now, when you plug in this minus 3.3 recurring into this number, and into this number, you'll get different numbers, which tells you that this solution is wrong. So again, you could do this method. You just need to be really, really careful when you get your numbers at the end. That's why I recommend to students get good at sketching them instead of trying to do them algebraically, because it's just easy to make mistakes. But you could do that if you really, really, really wanted to.